Hello class. Topic 29 is on the exponential of a matrix and how that's going to be useful in finding solutions where there are repeated eigenvalues. Now, preceding this topic, we have seen cases of solving planar and higher dimensional linear homogeneous systems of ODEs where the eigenvalues have been real and distinct, or they have been found in distinct complex conjugate pairs. We even saw a case where we had a repeated real eigenvalue, let's say an eigenvalue that was repeated 2 times, and if we are able to find 2 linearly independent eigenvectors for that eigenvalue, then we can also find an overall general solution. What we have yet to determine is a process or method whereby we can find all of the components of a general solution, even for those eigenvalues that are repeated. For example, if an eigenvalue is repeated 3 times, yet you can only find up to 2 linearly independent eigenvectors for that one eigenvalue, then we need to find a way to find that missing component for our general solution. If a system is n by n, then we must find n linearly independent total solutions in order to form the general solution. Okay, so our goal here in this topic is to find a way to produce general solutions when there are repeated eigenvalues. And we want this to be a way that is consistently gives us all of the linearly independent solutions that we are after to produce the general solution. Now, to accomplish this goal, we need to cover a little bit of theory. Let A be a square matrix. Given the Maclaurin expansion of e to the x, where x is a scalar, we can define the meaning of e to the at. Now, keep in mind that A is a matrix. Multiplying by a scalar t just means that we have a t next in every entry. So if the matrix was 1, 2, 3, 4, a 2 by 2, then AT would be t, 2t, 3t, 4t, a 2 by 2 with t's in all the entries. Well, the Maclaurin expansion that we learned in Calculus 2 is that e raised to the x can be expressed as 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4th, etc. It's a series that goes forever, and it converges for all x. We can define e raised to a matrix in a similar way. E to a matrix, e to the at, where at is going to be a matrix, in the same way that we did e to the x. Just replace all the x's that you see in e to the x with t times the matrix A. So we have TA right here, and then here we're going to have TA times another TA, and that just means that the t will be squared because it's a scalar, and then the a will be squared. So we wind up with t squared over 2 factorial times the square of the matrix A. And then we're going to get t cubed over 3 factorial times the square of the matrix, the cube of the matrix A, etc. And this produces a series of powers of matrices multiplied by scalars all added together. Also, I have to be clear that the 1 here becomes the identity matrix in our definition because these are all now matrices that are added together. Keep in mind that t times a is a matrix. Well, a squared is also an n by n matrix times this scalar, so this is just an n by n matrix. Same here, this is an n by n matrix. All of these terms are now matrices. In order for this addition to make sense, we have to add it to the identity matrix here. Therefore, e raised to a matrix is going to be a matrix again. That's important to keep in mind. The same dimensions as a. Now, in general, determining what e to the at is generally difficult, but there are cases where it's actually quite easy. For example, if some power of a will eventually be the 0 matrix, then we say that a is nilpotent. You don't need to know that word, but it just means that eventually a power of a will become 0. And when that happens, let's say it's a to the 4th and beyond that becomes 0, then the rest of the terms of the series, all these matrices over here are all the 0 matrix. So then our series expansion truncates and becomes just these first 4 matrices. And when that happens, we get therefore a pretty straightforward way to calculate e raised to the at. For example, let's see what happens when we want to find e to the at for the matrix below. We're going to explore this matrix by doing different powers of it and see whether or not it's nilpotent. So we're going to do a squared next, and feel free to get a matrix calculator out to speed some of these calculations up, but essentially I'm putting the matrix A next to the matrix A times A. So we're going to do 1 times 1 is 1, and then 1 times -1 is -1, add those together. So we get 0 in the 1, 1 position. Now we're going to do -1 times 1 is -1, and then add that to, that's going to be +1, and those also become 0. So we get the first column zeros out. In fact, we should get the exact same thing the second time because the two columns are the same. So when I use this column, I get one answer. When I use this column, I should get the same answer. And we're going to get 0 right away, the 0 matrix right away. So we get e to the at using our series expansion definition for what e to a matrix means is going to be the following. E to the at will be the identity matrix plus t times the matrix A plus, and then the rest of this is going to zero out because a squared is 0, which means a cubed will be 0 because the 0 matrix times a matrix will also zero out. So if a squared is 0, then so will a cubed be, etc. And we just get a whole bunch of 0 matrices after this. Therefore, all we have to do is now replace I with its 2 by 2 identity matrix. And then we're going to do t times A. The matrix A is 1, 1, -1, -1. We just have to distribute the t across there and then add the two matrices together. So we're going to add the components of the matrices together. We're going to get 1 plus t in the 1, 1 position. In the 1, 2 position, we're going to get 0 plus t, so just t. In the 2, 1 position, we'll get 0 minus t, so negative t. And finally, in the 2, 2 position, we'll get 1 plus a negative t, so 1 minus t. And so for the case of A being this particular 2 by 2 matrix, e raised to the at represents this matrix right here. Okay, next slide. Now, even when no power of A is the 0 matrix, in other words, suppose you start with a matrix A that's not nilpotent, we can sometimes still easily find e to the at. Now let R be any number and consider the following steps. Begin with e raised to the at. And what I'm going to do is I'm going to add and subtract a matrix to this exponent. I'm going to add RTI and subtract RTI. Now, keep in mind RT is just a constant, because R is a constant and T is a constant. They're scalars, I should say. And I is an identity matrix. So those two matrices we're going to group together and factor the T out. And this middle matrix here, we're now writing here in the front. And let's say, just so I have some letters to refer to these two, let's call that matrix A right there. And let's say that this is matrix B right here. Now, when you have e raised to the sum of two matrices, it can be shown that you can decompose that much like you would an e to an exponential. For example, e to the x plus y, we know that we can decompose to the product e to the x times e to the y. You can do that with scalars x and y. Can you do that with matrices? And I'm going to leave off the proof of this, but if these two matrices commute, if a times b is the same thing as b times a, then you can do that. So this is true because AB and BA commute. And that's simply true because A is a multiple of the identity matrix, and the identity matrix always commutes with another matrix. Okay, so we're able to decompose this into e raised to this matrix times e raised to this matrix. Now, furthermore, it can be shown that when you do the series expansion of this, it winds up being just e to the RT times the identity matrix. And so I'm able to change this step right here to e to the RT, which is a scalar, times the identity matrix. And this equation right here, this equal sign is true because this matrix A is a multiple of I. And then, of course, now we have a scalar right here times a matrix I times, and this still represents a matrix here, and identity matrix times another matrix, you don't need to write the identity matrix. So the I, you can just not write. And so we wind up producing this statement right here. So e to the at can be decomposed to e to the rt, which e to the rt is a scalar, times e to the t times matrix A minus r times identity matrix. So this part right here is still a matrix, and this right here is a scalar. And this can be done for any value, any real number r that you want. Now, if A is an n by n matrix, and r is an eigenvalue with multiplicity n just means that that eigenvalue is repeated n times, then the series for e to the t times A minus ri will truncate. So in other words, if r happens to be a eigenvalue, and it's the only eigenvalue for an n by n matrix, therefore it's repeated n times, then it's going to turn out that this series expansion for this matrix is going to truncate. And when that happens, when the series truncates, then we can easily find e to the at. So let's show how this happens in this case here, where we have the matrix A, which is 1, 1, negative 1, 3. Yeah, the first thing you want to do is find the eigenvalues. We're going to find the determinant of and remove r from the main diagonal, and then the other entries just rewrite, and then do that determinant. We're going to set this determinant equal to 0, and we're going to get 1 minus r times 3 minus r, and then minus negative 1, so plus 1. And then when I FOIL this, I get r squared minus 4r plus 3, and then we're going to add that 1. So we're going to wind up with plus 4 is equal to 0, and this does factor into r minus 2 times itself. So our only eigenvalues in this are 2, so both eigenvalues. So this is the case that satisfies that we have an n by n matrix, a 2 by 2 matrix. We found one eigenvalue, which is 2, and it has the same multiplicity as the dimension. Okay, when that happens, then we know that we can find e to the at by rewriting it this way here, using r to be that eigenvalue, and then write this part here as a series expansion, and then you will see it truncate. Okay, so let's do that part next. So we know that e to the at, in this case, will be equal to e to the 2t, e to the 2t is just a scalar, where 2 is the eigenvalue, times e to the t times the matrix A minus 2i. Now it's this part here that we are going to write as the series. So we can write this as e to the 2t times identity matrix plus, and we have t times a minus 2i plus, then we have t squared over 2 times a minus 2i squared plus, and this continues. Let me go ahead and give myself a little bit more room to write one more term just to make sure we understand the pattern here. The next one to be t cubed over 3 factorial times a minus 2i to the third plus, etc. And this goes forever unless it truncates. And to see where it's going to truncate, we want to start doing powers of a minus 2i and see when we get the 0. When is it that we're going to get the 0 matrix? So let's do those powers right over here. We have a minus 2i. So we're going to rewrite a minus 2i, remove 2 from the main diagonal, and that gives us a negative 1 in the 1, 1 position and 1 in the 2, 2 position, and the other positions don't change. So there's a minus 2i. Now let's do a minus 2i squared. And when you multiply these two matrices together, or you multiply this matrix with itself, I should say, I will let you confirm that we do in fact get the 0 matrix right away. Okay, so if we look at our series expansion, that means that we're going to get 0 matrix right there. This will be the 0 matrix as well. In fact, every term after this will just be the 0 matrix. So all we have to do are these two terms, and then multiply that by e to the 2t. Let me move this work over just slightly. So we have e to the 2t times the identity matrix. So we have 1, 0, 0, 1 plus t times a minus 2i. A minus 2i is negative 1, 1, negative 1, 1. So multiplying these together, we're going to leave the e to the 2t factored out, and then adding these two matrices together, we're going to get 1 plus or 1 minus t in the 1, 1 position. We're going to get t in the 1, 2 position, negative t in the 2, 1 position, and then 1 plus t in the 2, 2 position. And now all we have to do is multiply e to the 2t through there, or you can leave it factored out, but if we multiply it through there, it would simply multiply to every term. So here's your 2 by 2 matrix that's going to be e to the at for this case. Now, regardless of how or whether e to the at is even determined, it can be shown that the columns of e to the at form a set of linearly independent solutions to x prime equals ax. And because the columns of e to the at form a set of linearly independent solutions, that makes e to the at a fundamental matrix. Now what that means, again, if you remember, so let's go back up to this case here. If there had been a system, let's say the system was x vector prime is equal to, and then this matrix A, which is 1, 1, negative 1, negative 1, times the vector x. This was our system that we're trying to solve. If you can find e to the at, which we could in this case, then this is a fundamental matrix, meaning that the columns of it form the linearly independent solutions that we're after to make the general solution. So I would know that the general solution of this one here would be some constant, C1, times the first column of our fundamental matrix, which is 1 plus t and then negative t, plus some other constant times the second column, so t and then 1 minus t. Right, so this would be our general solution for this system. If you have a matrix A for which you can find e to the at easily, then you've effectively solved the system. You just got to put constants in front of each column, and then you have your general solution. In this case here, that was also the case. So if we had started with a, I'm not going to write it out this time, but you can do that if you'd like. But if there had been a system that was x vector prime equals this matrix A times x vector, and we were able to find e to the at like we did here, then you would say C1 times the first column plus C2 times the second column, and that will form your general solution to the system. In other words, that this matrix right here is a fundamental matrix to the system. I should also say that a system can have any number of fundamental matrices. If you recall, if I were to do a scalar multiple of one of these columns, then that would still be a solution to the differential equation. If I do a linear combination of these, I get another solution to the system of ODEs. And so by me calling this a fundamental matrix to the corresponding system, that doesn't mean that these are the only ways to represent two linearly independent solutions. It just means that this is one way to do it. Do any multiple of the first column plus any multiple of the second column, and you can form the general solution to the system. Now, keep in mind that e to the at is a matrix, and its columns are components of the general solution. So if you were to multiply that matrix by any scalar vector v, then you would produce a vector, right? Because a matrix times a vector is a vector, and it's going to give you a vector that is a linear combination of the columns of the matrix. In other words, if you take any linear combination of the components of a general solution will be another solution. So e to the at times v will be a solution to the system x vector prime equals a vector x for any constant vector v. We're going to verify this claim for the system below using the given constant vector. Okay, so here is our matrix A, and notice that was the first matrix A we did in our first example up here. It's the same matrix. So we've already calculated e to the at. So I'm going to borrow this, bring that down here. So we want to verify that e to the at times v times any vector v, and the vector v, this could be any choice here. I just randomly picked negative 2, 3 as my vector v. It could be any. So we have e to the at times the vector v is equal to, and here's e to the at. We've already done that from before. We're going to multiply that by the vector v, which is negative 2, 3. So keep in mind that just means we're going to do negative 2 times the first column plus 3 times the second column. So we're going to be doing a linear combination of the two columns of this matrix, which is why if you take two solutions and do a linear combination of them and your system is homogeneous, which it is, then of course you're going to get a solution again. So we're just going to confirm this though by calculating this and then showing that the result is a solution. It'll satisfy the differential equation. Okay, so we do negative 2 times the first column minus t plus 3 times the second column, and combine these together. I'll do a lot of this work in my head. Negative 2 times the first component there times the 1 plus t plus 3t. That's going to give me negative 2 minus 2t, but then add 3t. So I'm doing this distribution and this distribution, and then combining the results and doing that work in my head. I get negative 2 plus t. I'll let you confirm that. Now I'm doing negative 2 times negative t, so that's 2t, and then distribute this 3 across there, plus 3 minus 3t. So we have 2t plus 3 minus 3t. That's just going to be 3 minus t. So this is a solution. We're going to verify it by rewriting this differential equation. Vector x we're going to say is xy. Okay, so this is our differential equation, actually writing out the vector. But then when you multiply and then you set the components equal to each other, it turns into this system, right? X prime is equal to x plus y, and y prime is equal to negative x minus y. So here's our system of ODEs, and we're claiming that this is a solution. So the first entry is our x, so x of t, right? X is a function of t is negative 2 plus t, and the derivative of that is going to be just 1. We're saying that y of t is equal to 3 minus t, and the derivative of that is equal to negative 1. So we're going to replace all these things into our system and see if we get true statements. So let's verify the first line. X prime is just 1, and x plus y. So here's x, negative 2 plus t, and we're going to add that to y, and y is 3 minus t. Add these together, the t's cancel, negative 2, check. We get that first statement's true. Now let's do the second statement, that y prime is equal to negative x minus y, and y prime is just negative 1, it's a constant. So we get negative 1 on the left, and we do negative x, so we do negative of negative 2 plus t, and then subtract, and then y, which is 3 minus t. And so we're going to get 2 minus t minus 3 plus t. The t's will cancel. We have 2 minus 3. We get negative 1. Check. It works out. Okay. All right. Let's keep moving forward. Now, all this stuff is going to combine to inform a process whereby we can find all the linearly independent solutions that we need for any repeated eigenvalue. So let R be a real eigenvalue repeated n times. And by the way, this process generalizes if R is a complex valued eigenvalue. That's repeated. But we're going to stick this lecture to only repeated real eigenvalues. The process below will produce m linearly independent solutions. Okay, so first of all, r is repeated m times. If r was repeated only once, then it would be a distinct eigenvalue, and we would find that would produce only one of our components of our general solution. But if r is repeated 2 times, then we need it to contribute to 2 components of our general solution. If r is repeated 3 times, then we need it to contribute to 3 components of our general solution, so that our n by n system ultimately has n linearly independent solutions that can be combined to form the general solution. Okay, so what we're going to do is we're going to do a minus r I raised to the m and set it equal to the 0 vector and solve for all vectors v that make this true. And we are guaranteed at this point that we can find a total of m linearly independent solutions to this. And these solutions are vectors, and these vectors are called generalized eigenvectors. If this m was a 1, then the v here would just be called an eigenvector. But as you do different powers, if that's a square and a cube, and you then solve the resulting system of equations for v, then you're finding what are called generalized eigenvectors. Okay, now once you find those m generalized eigenvectors, then for each generalized eigenvector vi, so you'll have v1 through vm, a total of m of them, and they have to be linearly independent, then you're going to form a solution to the system of differential equations as shown below. We're going to fill this in here. And then this process that we have yet, that I'll show you here in a moment, this process will produce all m of the linearly independent solutions to the system that correspond to the eigenvalue r, which was repeated m times. Okay, we're going to begin by rewriting this statement here. We have e to the at times the vector vi. I'm going to write e to the at as, hearkening back to a few slides back to this line right here. I'm going to rewrite e to the at as e to the rt times e to the t parentheses a minus ri. I'm going to rewrite it that way where r is our eigenvalue. That's been repeated. So we get e to the rt times e raised to the t times a minus ri. And then, of course, we still have times the vector vi. Okay, the next thing I'm going to do is do the series expansion for this part right here. Now, e to the rt is just a scalar, so we'll leave that alone. So we have e to the rt times, and then we have the identity matrix plus t times a minus ri plus t squared over 2 factorial, or just over 2, times a minus ri squared, etc. And then times this vi component. Okay, now you can distribute the vector vi through here. So we have e to the rt times the identity matrix. We're going to do identity matrix times the vector. Well, multiplying by the identity matrix doesn't change anything, so we have just the vi vector to begin. Vi plus t times a minus ri times the generalized eigenvector vi plus t squared over 2 times a minus r identity matrix squared times vi plus etc. Now keep in mind that these VIs, these generalized eigenvectors, are solutions to this system, meaning that there's going to eventually, when we get to the mth power and we multiply by this vi, we should get the 0 vector back. So we do expect truncation to occur. So this will truncate, and it'll truncate. It might truncate sooner, but it'll certainly truncate by the time we get to the power m. So this means that our truncation is predictable. We'll get e to the rt times, I'm going to rewrite or copy this stuff here, and where do we expect the sum to stop? It'll stop prior to the m power term. So we'll get as far, maybe not as far, but at most as far as the term that looks like the following: t raised to the m minus 1 over m minus 1 factorial times a minus ri to the m minus 1 times this generalized eigenvector vi. And all the terms after that one will certainly be 0. And it's also possible that some of the terms towards the end might zero out sooner as well, but certainly after. Okay, and since we know that e to the at is a fundamental matrix, multiplying it by any vector will certainly give us a solution, a specific solution. And as we cycle this vi through the m different linearly independent solutions we got, we are going to wind up producing linearly independent solutions that can be used to form our general solution. Okay, let's do some specific examples. That's what the rest of this lecture is going to be, repeating this process, but for some specific examples, and we'll use some technology to speed some of these parts up. Okay, use generalized eigenvectors to find the general solution to the system below. Okay, the first thing we want to do is to find the eigenvalues. We can use technology to do it, but let's go ahead and just do this one by hand real fast. We want this determinant to be equal to 0, and when we FOIL these together, we're going to get, it's going to be r squared plus 4r plus 3. And then we're going to go minus this -1, so minus -1, so plus 1. And that gives us r squared plus 4r plus 4 is equal to 0. Which factors? We have r plus 2 squared is equal to 0, so we have both eigenvalues they're repeated. R1 and R2 are both the same. They're both -2. Okay, now for each eigenvalue that gets repeated, so let R be a real eigenvalue repeated m times. So R is -2 and it's repeated twice. So we're going to go through the motions of these steps here, where my R I'm going to use is -2 and the m's are 2. Okay, so step 1, we need to find the mth power of a minus ri, where r is -2. So let's begin by doing this. A minus ri, so a plus 2i, because r was -2, is equal to, so we need to add 2 to the main diagonals of this matrix. So add 2 to -1 is 1, and add 2 to -3 is -1, and the other entries stay the same. So there's a plus 2i. Now we want to do a plus 2i squared, and we're going to stop here, because we only have to go up to when m is 2 in this case. So we stop at this square. And when you multiply this matrix with itself, you're going to get the 0 matrix. Now what you want to do is we want to solve a plus 2i squared times a vector v will give us the 0 vector. So I'm going to use an augmented matrix to represent this. So I'm going to put a plus 2i squared, which is the 0 matrix, and then that bar that represents the equal sign, and then the 0 vector on the other side. We're trying to figure out the solutions to this system. Now notice that this is already in reduced row echelon form, so there really is no row operations to perform at this point. We just want to now identify the solutions. And keep in mind that x and y, notice there's no leading ones anywhere. So x is free and y is free, because both of the first two columns are missing a leading one. They don't have any leading ones. So x and y are free, which means that our solution is simply xy, where x and y could be anything. And then we break it apart. We say x times 1, 0, plus y times 0, 1. Since x and y could be anything, then it's the 1, 0 and the 0, 1 that are going to be our linearly independent two eigenvectors, generalized eigenvectors. So this will be our v1 and this will be our v2. And they are independent because they're not multiples of each other. Now when you multiply this matrix by a vector and get 0, then it should be obvious that the 0 matrix times any vector will give you the 0 vector. And so we can really just pick any two vectors that are linearly independent. So, I mean, it's possible, just to show you variety, I could also say that v1 is 1, 1, and v2 is 7, -5. These vectors are also linearly independent, and they can also be used as your generalized eigenvectors. But v1 and v2, as they currently are defined, are the most simplistic. 1, 0, and 0, 1. Okay, so we've done step 1. We were looking for two linearly independent solutions to that system. We found them, 1, 0, and 0, 1. And then step 2, for each of them, we form a solution to the system of differential equations as shown below. We're going to begin to write this out. In fact, let me go ahead and copy this. Now let's go through step 2. So I want to find I'm going to write my x1, my x vector 1 that is. The solution 1 can be found by doing e to the at times vector 1, where vector 1 is this generalized eigenvector right there. But we're going to go straight to this bottom line right here, and these i's will be 1s. So here's our expansion, but we know that vector 1, or this right here is the 0 matrix. But even if it wasn't the 0 matrix, we know that a minus ri squared times this vector 1 is 0, because vector 1 is a solution to solving this system right here, right? When you put v1 right here, you get the 0 vector. So this term right here will 0 out. And I should also replace these minus r's with plus 2's. Okay, so we have plus 2 there and plus 2 there. Okay, so with vector 1 times this matrix here will be 0. So that's going to 0 out, etc. So we truncate right there. So everything past that is 0 as well. So this will boil down to, oh, an r, I need to replace this r here. That was a negative 2. So we get e to the negative 2t times vector 1, where vector 1 is 1, 0. I should write that in there. Plus t times a plus 2i. A plus 2i was this matrix right here, so we can just copy that. There's a plus 2i times vector 1, which is 1, 0. And then everything else zeroed out, so I don't need to write anything else past that. Now I do have to do some matrix vector multiplication right here. And then also multiply by this t. Well, I'll leave the t factored out to the front, but let's see what 2 by 1 vector we get right here. Remember, a 2 by 2 times a 2 by 1 will be a 2 by 1. And we're going to get simply a 1, 1. Okay, so next, e to the negative 2t, and let's see what vector we have sitting here right next to this. We have 1, 0 plus t times 1, 1, so that's going to give me 1 plus t in the top position, and the bottom position is just going to be t. Okay, so here's my x1. Now let's find x2. Now x2, a lot of this is going to be repeated. So copy, paste, shrink that down just so I can fit it in here. And you're going to see a lot of similar things happen here. The only thing that's going to be different is we want these subscripts to all be 2's now. So x2 and v2, that'll be v2, v2, and v2. Okay. And we're still going to get truncation at the exact same moment, because v2 is also a solution. v2 times this matrix right here, this will be the 0 vector, and every vector after that will be the 0 vector. Okay. And then v2, of course, is not 1, 0, but 0, 1. So let me change some of these things, and let's see how this affects our answers. So we have 0, 1 is v2, 0, 1 is v2. So we get 0, 1 here, and then multiplying 0, 1 times our matrix gives me negative 1, negative 1. Now putting these together, we get negative t and then 1 minus t. And this is our x2, our second linearly independent solution. So we have one solution, a second solution. They are linearly independent, and so we do get to together make the general solution by doing c1 times first solution plus c2 times second solution. And this is our answer, effectively. I ran out of space, otherwise I'd write out what x1 and c1 are. But here we have created a general solution to this system that had a repeated eigenvalue. Okay, let's go on to the next example, which is a 3 by 3. Now, I've already taken the time to find what the eigenvalues are. The eigenvalues for the system below are given. Find the general solution. Okay, so we're going to begin by recognizing that we have a repeated eigenvalue of negative 2, and it's repeated twice. So m is 2. So I'm going to want to do powers. I'm going to want to do the second power of a minus negative 2i. So let's begin with a minus negative 2. So a plus 2i is the matrix. Remove 2, or sorry, add 2 to all the main diagonal. So we get 4, and I'm just focusing on the main diagonal right now. 4, 1, negative 4 is the main diagonal. Add 2 to all the entries on the main diagonal. All the other entries stay the same. And we want to go 1 power of this higher, because this eigenvalue is repeated twice. So I'm going to multiply this matrix times itself. Okay, notice that when I raise this matrix to itself, I wound up getting the same matrix I started with. This is an interesting phenomenon. But we also are assured that I should be able to find 2 linearly independent solutions when I set this equal to the 0 vector. So now I'm going to make my augmented matrix. Get rid of that, make an equal sign, put the 0 vector over here, and we want to solve this system. I can use this middle column right here, middle row I should say, to 0 out the rows above and below, because they're identical. Like if I do negative 2 times the middle and add it to first and third rows that should zero out, and then I'll finish with a row interchange. So we have 2, 1, negative 2, 0 at the top, and then all zeros for the other two rows. Now, I'm not going to bother making this a 1 because I don't want to introduce fractions. I could divide everything by 2 in the top row, but let's avoid the fractions. And so we do have a leading entry. It's not a leading 1, but it is a leading entry. I could make it a 1 if I wanted. That's the x position. But the y and the z are missing leading entries. So they're both free. And if you have two free variables, that means you're going to find two linearly independent solutions. Right? The number of free variables will dictate how many independent solutions you can get when you put in reduced row echelon form, or near reduced row echelon form, as is this case. So row 1 does translate into the following. 2x plus y minus 2z is equal to 0, and x and y are free. So if I were to write my x, y, z solution, y and z are free, then the first entry would be take this equation right here and solve it for x. So if we solve this for x, we would get 1/2 of negative y plus 2z. And I could distribute that half. So we get negative y halves plus z. And then y is free and z is free. So if I were to separate this apart and organize it by free variable, we would have y times negative 1/2, 1, 0, plus z times 1, 0, 1. So you can use these two vectors now. This is the v1 and this is the v2. These are our two linearly independent generalized eigenvectors that are associated with this eigenvalue of negative 2. Now you can do also any multiple of them, and so and avoid the fractions there, and let's just double that vector there and go with vector 1. Generalized eigenvector 1 is going to be the double of this one, right? Because any multiple will work. Just double that, so it's negative 1, 2, 0. And our second generalized eigenvector will be this 1, 0, 1. Okay, now we want to continue with forming our general solution. Keep in mind, so far I've only been analyzing this repeated eigenvalue. So this repeated eigenvalue that got repeated twice, this negative 2 got repeated twice, we want to find two linearly independent solutions to the system so that we can then use this third eigenvalue to find the third, and then we'll have our three total linearly independent solutions that will form our general solution. Okay, so x1, vector x1, first solution will be e to the rt, so negative 2t. So we get e to the negative 2t. Vector 1, this is a 3 by 3 now, so vector 1 is this negative 1, 2, 0 that we have there. Negative 1, 2, 0, plus t times a plus 2i. Here's my a plus 2i, copy that, times vector 1, which is negative 1, 2, 0, and then nothing else after that. So we can just end our brackets. Okay, now we have a matrix vector multiplication to do right there. And we do negative 1 times 2, negative 1 times 4 is negative 2, or negative 4, plus 4 is 0, plus 0, so we 0 out the top entry. Negative 1, 2, 0 will 0 out the bottom entry, and negative 1, 2, 0 will 0 out the last entry as well. So we did get, this one would have truncated even sooner. Got the 0 vector back. And that's not surprising because if you recall, a plus 2i wound up being the same thing as a plus 2i squared. So when I said a plus 2i squared equal to 0 and found two linearly independent solutions, that they were also solutions to just a plus 2i is times the vector is equal to 0. So we actually would have had this part truncating as well. So that should be 0. And then x2, change the subscripts on the v's to 2's. That's the only difference. And plug in vector 2, and you're going to see something similar. Vector 2 will also 0 out this matrix because vector 2 zeroes out the square of that matrix, and the square of that matrix is the same as that matrix, so we're going to get a 0 truncation here as well. So we really just get v2 times v2, and v2 is 1, 0, 1. Now to find the third one, I'm going to just use technology to go ahead and get it. The eigenvalue is negative 1, and there's an eigenvector that goes with that one here. So let's say our third solution, x3, is going to be e raised to that eigenvalue, so negative 1t, so just negative t, times the eigenvector associated with it, which I'll leave you to use Wolfram Alpha or something to find it. I'm going to save some time during this lecture and not derive it here by hand. But 2, 1, 2 is its eigenvector. And there's our third component. And so our final general solution will be C1 times the first component, which is e to the negative 2t, times the vector negative 1, 2, 0, plus C2 e to the negative 2t times its the next generalized eigenvector 1, 0, 1, and then plus the C3 times the e to the negative t times 2, 1, 2. Now I want to point out something about this example. We saw that we had a repeated eigenvalue of negative 2, and we went straight to this process illustrated here on this slide. However, this process isn't always necessary when you have repeated eigenvalues. It's a process that will always work, but it isn't always necessary and can often feel a little bit more lengthy to execute. If I had simply tried to find the eigenvectors associated with the eigenvalue negative 2, I would have set this matrix here equal to 0 and solved, and I would have found these exact same two linearly independent eigenvectors. So these two are actually eigenvectors associated with negative 2. They're not generalized eigenvectors. And that doesn't always happen. It happened in this case. And this process here is not necessary when you have a repeated eigenvalue that produces as many linearly independent eigenvectors already. And since negative 2 in this case was an eigenvector repeated twice, an eigenvalue, I should say, repeated twice, when I find the corresponding eigenvectors, I would have found the same two linearly independent eigenvectors, which would have allowed me to go straight to this solution in the first place. E to that negative 2t times one of its eigenvectors, and then e to the negative 2t times a second linearly independent eigenvector. So using generalized eigenvectors wasn't necessary here. Okay, let's do just a couple more here. Find the general solution to the system below. This one does not give you the eigenvalues, so let's do this one by hand. So we're going to find the determinant of a 3 by 3 that's removing r from the main diagonal. Every other entry is the same, and we want that determinant to be 0. We're going to use cofactor expansion, but all the zeros here, like when we do the first, cross out the first row and column, all those, that's going to be the only one we have to calculate because there's zeros in the remaining entries of that column. And the 2 minus r that I just crossed out is in a positive position, so we really just get a determinant of 2 minus r times the 2 by 2 determinant. And now we just have to do that product minus that product. Well, that extra 0 there really just winds up producing a 2 minus r cubed is equal to 0. So this gives us that all of our r's are 2. So we have a repeated eigenvalue. It's repeated 3 times. So the next thing I want to do is start doing powers. I want to do a minus 2i, figure out what that is, remove that eigenvalue from the main diagonal. So remove 2 from the main diagonal gives me a main diagonal of zeros now. And there's a minus 2i. Now let's start doing powers of this. I have to go up to the third power. Fortunately, these powers will be easy to compute. When I do the first power, and I'll leave it to you to verify, you should get 0, 0, 0 in the first 2 columns. And in the last column, we will get negative 6, and then 0, 0. So we get practically all zeros when I do this power here. And now let's go to a minus 2i cubed. And I have to go up to 3 because this time our eigenvalue is repeated 3 times. So the m is 3. So we go up to the third power. And if I do a third power, we will get the 0 matrix, a 3 by 3 of all zeros. So when I now solve the system, all zeros here, that's a 0, not a 6, we see that x, y, and z are all free. So really, I just need to find 3 independent solutions. I need to find 3 vectors that are linearly independent so that when I multiply it to the 0 matrix, I will get the 0 vector back. Well, I can pick any 3 vectors. So I can just go with the most simplistic ones. The first vector I'm going to pick is 1, 0, 0. The second vector I'm going to pick is 0, 1, 0. And the third vector I'm going to pick is 0, 0, 1. This is exactly what you would get if you had said x, y, and z are all free, and then ripped apart x, y, z as x times this vector plus y times this vector plus z times this vector, and then use those vectors as your three generalized eigenvectors. And now we are ready to make the actual solutions. Okay, let's see what happens when we do this. Let me move a little bit of work around here. Okay, here we go. The first solution, x1, is equal to, it's going to be e to the rt, so e to the 2t, times v1 plus t times a minus 2i times v1 plus t squared over 2 times a minus 2i squared times v1. And then we're going to get truncation after that, because v1 is, when you multiply v1 to a minus 2i cubed, we get 0. All right, so we get e to the 2t. v1 is 1, 0, 0. Then we have to do a minus 2i. So a minus 2i is this matrix right here. And that needs to be multiplied by v1, which is 1, 0, 0, plus, and then we have t squared over 2, and then we have a minus 2i squared, which is this matrix right here, and that needs to be multiplied by v1, which is 1, 0, 0, and we will stop. So we have to do a few matrix vector multiplications, and these are all pretty easy ones. When you multiply these, they will zero out. When you multiply these, they will zero out. So we will get 0 and 0 for both of those. So we really just get this first part right here. We're going to get e to the 2i, e to the 2t times just the times v1. There's my first solution, my first component of my general solution. Okay, for the second one, let me just do some copy paste. Only difference is going to be that these are going to be v2s now, which means the roles of the 1, 0 will switch, because v2 was 0, 1, 0, 0, 1, 0, 0, 1, 0. Okay, 0, 1, 0, this will not zero out right here, but this one will still zero out. So we're still going to get 0 for this last part, but we are going to get a non-zero result here in the middle. Let's make some changes. We have 0, 1, 0 plus t times, and now let's do this matrix vector multiplication, and we're going to get negative 2, 0, 0. So this will form, we can actually group this together. So we have e to the 2t, and we have 0 plus, so we have negative 2t, and then we have 1 plus 0, so just 1, and then a 0. So there is our second linearly independent solution. Now we want to do this, oops, I forgot to change this subscript, that should be x sub 2. One of these, and paste it, and let's find x sub 3. Okay, so what's going to be different? This will be a subscript of 3 now, x sub 3. This will be v3, v3, and v3. And v3 is, we need to switch those around. 0, 0, 1, 0, 0, 1, 0, 0, 1 is v3. And making my other adjustments. Okay, so this time times the t, we're going to get 0, 0, 1. So when I do this product right here, this matrix times that vector will give me the last column of the matrix, so 1, 3, 0. And then we have plus t squared over 2 times, and we don't zero out this time over here, and so we're going to multiply these two together, and we get negative 6, 0, 0. Okay, so this time when I shove all three of these vectors together into one vector, all right, we're going to get 0 plus t minus 3t squared. So t minus 3t squared. And then 0 plus 3t plus 0, so just 3t will be the next. And then the last one will be just 1. Okay, so there are our three linearly independent solutions. And so our general solution will simply be, and I won't write them all out again, but c1 times the first one that we wrote up there, plus c2 times the second one that we wrote up there, plus, and that should be times, not plus there, and then plus c3 times the third component of our general solution, and there's our general solution. Okay, one more. Let's do a 4x4, and we'll use some technology to help speed up some of these results. And the eigenvalues are already provided. I'm going to also use technology to get the eigenvector associated with eigenvalue -1, and let's just do the process for these three repeated ones here. Okay, so the first thing we want to do is do powers of a minus And then I'm focused on the repeated eigenvalue, so we're using r as 1. So a minus 1i, so just a minus i. So remove 1 from the main diagonal of this 4 by 4. So we get 6, 0, negative 6, negative 2. And all the other entries are not going to change. Just make sure you don't do any copy errors, silly mistakes like that can happen. So there is a minus I. Now I'm going to use some technology to do my powers. So a, and we have to do up to the third power because this was repeated 3 times. So we do a minus I squared. And using technology, I got negative 8, 4, negative 4. Then that row of zeros is still there. Then negative 16, 8, negative 8. And then 8, 8, negative 4, 4. Now, I noticed something right here. That the process does say to go one step further, to go to the third power. And if I were to go to the third power, I would get 16, 16, negative 8, 8. A row of zeros again. 32, 32, negative 16, and 16. And then negative 16, 8, and negative 8. So I could now set this equal to the 0 vector and solve and find 3 linearly independent. I need to find 3 linearly independent generalized eigenvectors because this eigenvalue was repeated 3 times. But if ever in this process you find a smaller power that can lead to as many linearly independent eigenvectors that you need, then you can really just stop right there. And I noticed that if I put this matrix here in the middle into RRE form, so let's go RRE form, and this is actually easy to do to spot because noticing that I could use this row right here to effectively zero out that row and that row. If I were to do negative 2 times this row and add it to the third row, that would zero out the third row. And if I do negative 1 time, or if I just add the 2 rows, add row 1 to row 4, that would, to change row 4, that would cancel row 4. So I notice that I can easily get some zeros down here using the first row. And then I can then divide everything here by negative 4, perhaps. So in RRE form, or near RRE form, I could have a 2, 2, negative 1, 1, and then zeros everywhere else. Now, when I set this equal to the 0 vector, because all rows but 1 zeroed out, I know I'm going to have 3 free variables. We're going to have a non-free variable to start, but then 3 free variables there. And if you have 3 free variables at this stage in the game, then we can stop here, because we need to find as many free variables as I have the eigenvalue has been repeated, which is 3 in this case. Now, it'll be guaranteed that if I do go this far and put this in reduced row echelon form, that you're also going to get 3 variables, 3 free variables. And so it'll work if you proceed with this a minus I cubed. But if you can stop sooner and get as many free variables as you need to produce to match how often, or the multiplicity of that eigenvalue, which is 3, then you can stop sooner in the process. In other words, we're going to get truncation at a minus I squared and beyond. We don't have to go as far as a minus I cubed. All right, that's important because now we just have a lot less computation to do here. And I probably won't finish this problem entirely. I'll just get it set up for time's sake. But our first linearly independent solution that we're after is e to the, we're using these eigenvalues here. We're not focusing on that negative 1 just yet. So we do x sub 1 will be e to the 1t, so just e to the t, times vector 1. We still have to find what those vectors are, so I'll do that here in a moment. But vector 1 plus t times a minus I, and then the rest is going to zero out. Because I need a vector 1 here. I didn't write that correctly. I got to put a vector 1 next to that. Plus times vector 1, then zero out. Because I'm going to find a vector 1 from solving this, and that's going to zero out a minus I squared. So I don't have to do a third term and then expect the zeroing out. I can anticipate the zeroing out will occur sooner. The truncation will happen sooner than expected. So I'm going to not even bother with doing a minus I cubed and solving it. We are going to proceed to find v1, v2, v3 from this. So I'm going to take that first row this row right here and turn it into an equation. So we have 2x plus 2y minus z, and then we need another letter for the fourth dimension. We'll use w, so plus w is equal to 0. And y, z, and w are all free. So I just have to solve this for x. So x will equal to 1/2, and it's going to be negative 2y plus z minus w. So now we see that y, z, and w are all free, and x has to be a certain thing. So we can say our solution, x has to be, I'm going to distribute the 1/2. X has to be negative y plus 1/2 of z minus 1/2 of w. But y, z, and w are free. So when you break this apart, we have y times negative 1, 1, 0, 0, plus z times 1/2, 0, 1, 0, plus w times negative 1/2, 0, 0, 1. And so our generalized eigenvectors, we have 3 linearly independent ones, and we got it at 1 power sooner. We could have found them again here, but if we can find 3 from this stage, then you can stop at that stage, because the truncation will just happen sooner than expected. And we get v1 is equal to this first vector, negative 1, 1, 0, 0, plus, and then v2, our second generalized eigenvector that we're going to use. Again, if I want to avoid the fractions, you can just double this. So I'm going to give the non-fraction version of this, double everything. So we have 1, 0, 2, 0. And then my third generalized eigenvector, again, doubling everything, negative 1, 0, 0, 2. So these are the 3 independent generalized eigenvectors that I'm going to use in the creation of my x1, x2, x3. And I'm not going to spend the time to do these calculations. I'll leave it to you to do that. But you do want to find the other 2 with some changes, get rid of those subscripts and replace them with the appropriate subscript. So that's a subscript 2, that's v2, that's v2. This is a subscript 3, that's v3 and v3. Okay, now this was all the work that we had to do for the repeated eigenvalue. And we still have to do now what happens when your eigenvalue was the negative 1. Well, I went ahead and cheated and got that the corresponding eigenvector to this eigenvalue was 1, 0, 2, negative 1. So we can find our fourth linearly independent solution by doing e to the rt, so e to the negative t, times its eigenvector, which Wolfram alpha helped me to get, which is that component. So this work, that's what you'd have to do to find the solution corresponding to that eigenvalue. And now we are ready to put these all together, of course, and our general solution will be c1 x1 plus c2 x2 plus c3 x3, vector x3 that is, plus constant 4 times vector x4. And there's our actual general solution right there.